We've defined our problem, we've developed some solutions, and we've tested a prototype. Now we get to the final, most sophisticated step: optimization. This isn't about making a change that just fixes a flaw. It's about making a change that makes the entire design the absolute best it can be, using the least amount of time and money. The key to this is modeling, specifically using computer simulations and math to generate data quickly and cheaply. An engineering model is simply a stand-in for the real thing. Think of it like a weather forecast. It's a model based on math that predicts what the sky will do. In engineering, we use models to predict how our design will behave. If you're designing an airplane wing, you don't build a full-size wing every time you change its shape. You build a mathematical or digital model that can tell you in seconds what will happen. Models come in two main flavors. Physical models are things you can touch, like a small, scale version of a roller coaster. Then there are computer models or simulations. For optimization, computer models are often better. Why? Because you can change one number, say the thickness of a wall, and run the test thousands of times without wasting any materials or time. The reason we use these models is pure data generation. We set up the model to calculate performance numbers for us. If you're building a self-driving robot, your model can generate data on power consumption for different motor sizes. That data is crucial because it gives you hard evidence, a number, to decide if motor size A is better than motor size B for maximizing speed while minimizing battery use. Optimization requires clear targets. You need to explicitly define what you want to maximize and what you want to minimize. For a phone case, you want to maximize protection and aesthetics, but minimize weight and cost. Defining these opposing goals helps you understand the trade-offs involved and gives you a bullseye to aim for when you start generating data. Don't underestimate the power of simple math. The most basic and effective engineering model is often just an equation. If you're designing something that moves, you'll use formulas relating force, mass, and acceleration. These equations allow you to instantly predict a result. If you increase the mass, you know immediately how much more force is needed. They are a zero-cost, instant data model. When you use a physical scale model, you have to be very careful with proportionality. If your small model of a bridge is 1/10 the size of the real bridge, the forces acting on it might not scale down perfectly. Engineers use complex scaling laws to make sure the data collected from the miniature version accurately reflects what will happen when the final, full-sized product is built. Optimization is all about iteration, meaning we repeat the process over and over. We don't just test our design once. We develop a plan to systematically adjust one variable at a time. For instance, you test angle 10 degrees, then angle 12 degrees, then angle 14 degrees. You record the data for each run. This systematic, iterative testing is how you pinpoint the absolute best angle for performance. Let's look at a specific example: material thickness. If you're designing a frame, you want it to be strong but light. Using a model, you can run a quick simulation where you test 10 different thicknesses. You instantly get 10 data points comparing strength and weight. You'll probably find that a 4mm thickness is much better than 1mm. But a 10mm thickness is too heavy and only slightly stronger. Another common variable to model is the shape or geometry. Think of designing something that moves through the air or water. The difference between a block shape and a smooth teardrop shape is huge in terms of drag. Instead of carving out 10 different shapes, you use a fluid dynamics model on a computer to generate data on the drag coefficient for each design, showing you which one is the most efficient. Once you have mountains of data from your iterative runs, you have to analyze it to find the sweet spot. This is usually found by plotting a graph where one axis is your maximized goal, like speed, and the other is your minimized constraint, like cost. The optimal point is right at the top of the performance curve, just before the cost or weight becomes too high. Sensitivity analysis helps you understand which parts of your design matter most. You ask, if I change this part by a little bit, how much does the performance change? If a tiny change in the material composition causes the entire structure to fail, your design is very sensitive to that material. Knowing this tells you exactly where to focus your resources and time for modification. Engineers are always watching for diminishing returns. This is the point where the extra effort or cost you put in is no longer worth the small gain in performance. If it costs $50 to make a product 10% faster, that's great. But if it costs another $500 to make it just 1% faster, you've hit diminishing returns. Optimization means stopping before you cross that point of inefficiency. No matter how brilliant your data is, the optimal design must always satisfy the initial constraints. Your model might show that the strongest design uses a titanium alloy, but if your budget constraint said you can only spend $20, the titanium design is immediately disqualified. Optimization is about the best solution that exists within the rules of the project. For many of our simple mathematical models, a basic spreadsheet is the perfect tool. You can set up formulas where one column calculates the total weight and another calculates the total cost. By changing the values in one cell, say the thickness or density of the material, the entire spreadsheet instantly updates. This allows for incredibly fast and effective iteration and data analysis. The beauty of computer modeling is the speed. Instead of the hours it takes to build one physical prototype, a computer model can simulate hundreds of design variations in the same amount of time. This broad-scale testing means we're not just comparing 3 good ideas, we're comparing the optimal outcome from a huge population of potential solutions. It's important to remember that a model is not perfect. All models rely on assumptions, simplifications of reality. For instance, a computer model of airflow might assume the air is perfectly smooth and clean, even though the real air has dust and turbulence. Engineers must be aware of these limitations and always verify the final optimal design with a real-world physical prototype. The whole point is that your modifications must be data-driven. If the model data shows that the highest point of stress is at the corner joint, your modification is not to add a sticker. It's to redesign that joint to be thicker, rounded, or reinforced. The data from your iterative modeling tells you exactly what to change and by how much to get the maximum positive impact. Once you've settled on the final optimized design, you prepare a report. This report is your proof. You must show the data you collected from your model, illustrating the iterative path you took. You need to justify why, out of all the thousands of iterations you ran, the one you chose is demonstrably the best solution that adheres to the criteria and constraints. Optimization is the true heart of engineering. It's what separates a product that works from a product that changes the world. It's not enough to simply solve the problem. We must use modeling and iterative testing to solve it with the least waste, the greatest efficiency, and the most effectiveness. This is the skill that allows engineers to constantly push the boundaries of what is possible.